Before we dive into the control design, I want to show you what you will be able to simulate by the end of this video. On the left, you are seeing a ship moving in 3D. You can see it here. And on the right hand side, I have a top view of the same simulation result. In the beginning, there is a slight trajectory tracking error because I will be teaching you how to design a standard controller, and then you can build on that and improve the controller as you prefer. We will start from the mathematical model and work step by step through the design, and I promise by the end you will be able to do exactly this simulation. Or if you want to follow another trajectory, you will be also able to do that simulation. So let's go and design the controller for 3 degree of freedom ship vessel. This is our state space mathematical model for 3 degree of freedom ship control. You can see it has two parts. First one is kinematics and the second one is dynamics. So the goal of 3 degree of freedom ship control is to design control laws such that it achieves desired position. So we have two control inputs. One is tau u, one is tau r. This is actually a force, and this is a torque. Okay, and we have 6 measurable states. We have x, y, psi. So these are associated with the position. This is yaw angle. Okay, u represents surge velocity, v represents sway velocity, and this is yaw rate. So we have a 2 input and 6 output system. This model is a underactuated system. We can see that because the number of inputs, they are less than the number of outputs. And it is a challenge to design the control input for 3 degree of freedom ship because the goal is to control and achieve the position x and y, but it does not have any control inputs in these equations. So we have to control the position, which is actually part of kinematics, indirectly using dynamics. So what we are going to do is we are going to design control law and feed it to dynamics, okay, and then achieve desired velocities in such a way that it can control the kinematics, right? Because we have u and v appear in kinematics, and that can be controlled using the control inputs of dynamics. So we have to control this u, v, and r as well in such a way that we can achieve our desired control objectives. Now, for simulation purpose, I should tell you this, that we will be using Cybership II. We will be using this ship. It is developed by NTNU. Sorry, I don't know how to pronounce it, but it is developed by them. And we will use its parameters for simulation purposes. So once again, the goal is to achieve trajectory tracking. So we have two types of control designs. One is trajectory tracking. And the second one is path following. Okay. The difference is trajectory tracking, this depends on time parameter, but this does not depend on time. Okay. So path planning actually, if you already know how to control this, you will know that path planning is relatively easy than the trajectory tracking, because in trajectory tracking controls, the control law and all the objectives are dependent on time. So this is much more challenging. But the thing is, if you can do trajectory tracking control, you will eventually be able to do path planning easily. The aim of this lecture or this video is to design trajectory tracking controller. So let's proceed with the design. So to begin the controller design, let us define a tracking error. Let's say we have a desired position. Let me denote this with P of t. And we have desired position, right? And desired yaw angle, okay? And then we have desired velocities. So we know that velocities are actually the derivatives of position, right? And then desired yaw rate. So these are desired control objectives. So what we are going to do is, firstly, let's define a tracking error. So the tracking error is defined as x minus x desired. And we can similarly define it for the position along y-axis, y minus y desired. And similarly for this yaw angle, psi minus psi desired. Okay, we will need this later on. So just let's begin with this one firstly. Now the tracking errors need to be transformed to the body frame of the ship. So how do we do that? In order to transform our tracking errors to body frame, what we can do is that let's define a tracking error in this way for body. Okay, and let's do some matrices because use some matrices because we have this rotational matrix, right? We will be multiplying our tracking errors with rotational matrix to obtain the body frame errors. This is really key part. What is the rotational matrix? So the rotational matrix in this case is written in this way. So we have cos. So note this is minus psi. So we will be replacing the traditional psi angle with minus psi. And then we have minus sine minus psi. And then we have sine minus psi and cos of minus psi. So this will become like this, cos of psi. We know this property of cos angle. When negative, the angle is with negative sign, so this is automatically removed. So we obtain this cos psi. For sine, it becomes minus psi. And let me write it over here. So cos of minus theta is actually cos of theta. And sine of minus theta is equal to minus sine of theta. These are properties of angles. Okay. So what happens with this is that this will become minus sine theta, and then we have minus over here before that. So this will become sine of psi. This will become minus sine of psi, and this will once again be cos of psi. Now, please ignore this. Okay, so when we multiply this with this tracking error, what happens is that we obtain our body and along x-axis, and y-axis becomes cos of psi, sine of psi, minus sine of psi, cos of psi, multiply with tracking error along x-axis and y-axis. So exb in body, I mean, becomes ex cos of psi plus ey sine of psi, and e body, y body becomes minus ex sine of psi plus ey cos of psi. So these are our tracking errors in the body frame, right? So now let's move to the control design. And for that, actually, we are already doing the control design. Now let's move to the next step where we have to take the derivative of these tracking errors. So let's go to the next slide. So what we are going to do is we are going to take the derivative of these tracking errors. So let me rewrite this error along x-axis in body as ex body is equal to ex cos psi
plus Ey sine of psi. Now its derivative can be derived like this. We know the product rule of derivatives, right? So we have two terms over here and then two terms in this one. So what we are going to do is we are going to simply apply the product rules of derivative like this. So this becomes first derivative of second. So derivative of cos is actually minus sine of psi. Okay, and then derivative of this angle. So this becomes psi dot. Then plus second term cos of psi and derivative of first. So this becomes ex dot, right? Now moving to the second term, we have first, right? Derivative of sine y, sine psi is cos of psi and derivative of the angle, right? Plus derivative of the first one. And then sine stays as it is. So this is for the first term before addition, and this is for the second term. Now what we are going to do is that we are going to simply substitute this psi dot. If you remember from kinematics, this was equal to r, and then we will do the simplification. So this will become minus ex sine psi. This psi dot will be replaced with the r, so this will be r plus ex dot cos psi. This stays as it is. Let's see what we can do with ex dot. We will see that later on. This becomes Ey cos psi r plus Ey dot sine of psi. Okay. Now let's rearrange these terms together and this r with this one. So this becomes Ex dot cos of psi plus Ey dot sine of psi. Okay, and this will become plus r minus sine of psi plus Ey. This one become cos of psi, right? So what we are going to do is that we are going to write it Ex dot cos of psi plus Ey dot sine of psi plus r, and this is actually Eyb. If you go back to the previous page, you will see this, that this term is actually equal to the tracking error along y-axis in body. So this is simply written like this. So we have achieved this Ex dot of b. Now the thing is, how do we solve this one, Ex dot and Ey dot? So we can simply take its derivative. We know that Ex dot is equal to x dot minus x desi dot, right? If you recall, we had Ex is equal to x minus x desired and Ey equal to y minus y desired. So we simply directly take its derivative, and similarly for Ey dot will be y dot minus y desired dot. So now I will substitute these values in the body frame tracking errors. So this will become equal to, let me rewrite this equation so we can do it much better. Okay, so now I simply have to substitute these values. So this will become x dot minus x desi dot times cos of psi plus y dot minus y desi dot times sine of psi plus r e by b. Simple multiplication. So x dot is equal to cos of psi minus x desi dot cos of psi plus y dot sine of psi minus y desired dot. This is y d, okay? This is y d sine of psi plus r EYB. Now from the kinematics, we know this x dot equal to u cos of psi minus v sine of psi, and y dot was equal to u sine of psi plus v cos of psi. So I'm going to simply substitute these values in the Ex dot in the body frame. So please note this is in the body frame. So this will become u cos of psi minus v sine of psi. Okay, and this will be cos of psi minus x psi dot. We don't know this, so we will write it as it is, plus y dot. So this will be u sine of psi plus v cos of psi, right? And then this sine psi, right? And then y psi dot sine of psi plus r e y b. Okay. So now we simply have to do the multiplication. This cos psi will be multiplied with this one. So this becomes u cos square psi minus, now it will be multiplied with this one. So v sine psi cos psi. Okay. I will write this at the end. So let's do this multiplication first. So this will become u sine square psi, right? Plus v cos psi times sine psi. And now let me write this minus x psi dot cos psi, and this minus y desired sine psi plus r e y b. So now the rate of change of tracking error along x-axis in the body frame, it will be derived as Ex dot b equal to u cos square psi plus sine square psi minus, and two terms were cancelled out, which were minus v sine psi cos of psi plus v cos of psi sine psi. So these two terms were cancelled out, and then we had these terms with derivative. So I will write with minus as a common. So x psi dot times cos of psi plus y psi dot sine of psi, and then we have this term plus r e y b. So this is actually equal to 1 due to the property of angles. And let's denote this with u desired in body. So Ex dot b is equal to u times 1. So this will be u minus u desired body plus r e y b. Okay, so this is the rate of change of x in the body frame, and we obtain this equation. Similarly, what we have to do is we have to do the same process for e derivative of b. So we had this equation for e dot in body frame for y-axis. So I will not do all of its calculation here because it follows the same pattern, same derivation, and I will just simply write the equation over here, and then you can confirm it yourself. If you are struggling with it and you are unable to find it, then you can let me know in the comments and I will send you the full solution. So this equation becomes v minus v desired of b minus r e b. So here, but we will have x or y. I will leave that to you. Okay, leave your answers in the comments and I will let you know if you have derived it correctly. So now we have these tracking errors. If you remember, I had already defined this tracking error for the yaw angle as well. So why is that important? We will know that up next, but let me derive that. It is really easy. We had this Ey is equal to psi minus psi desired. So its derivative become psi desired dot minus, psi dot minus psi desired dot, and this is equal to R from the kinematics, and this is psi desired dot. So I will call this as RDB, that is in the body frame. So E psi dot becomes RDB, right? R minus RDB. Let me rewrite this equation. Erase it. So this becomes R minus RDB. Okay. Now, why is this equation important? If you remember, we had control input in in V dot, there was no control input, and in R dot, we had this control input dot R, if you recall the dynamics. So what we are going to do is we are going to choose this U as a virtual input to the system. So let me explain that in the next slide. I will rewrite the kinematics and dynamics and explain it to you. So let's go to the next slide. So we derived these three equations. Let me rewrite it over here. We derived the tracking errors in body frame for positions, and let me rewrite it here. Ex dot b is equal to u minus u desired in body plus r e y in body. V desired in body minus r e in body. I know this, but I will leave that to you. And then I derived E psi desired dot. E psi dot is equal to R minus R desired in body. So why I derived this? This is really important, because if you look here in U dynamics, we have this control input. In sway velocity, we don't have any control input, and in yaw rate, we have this controller once again. To control the kinematics, actually this U and V and R, they are actually appearing as virtual inputs. So if we can control this U, V in such a way that it can result the desired position, so we can achieve our trajectory tracking mission. So we will not be doing this control for like achieving stability. For example, for this dynamics, I want U to approach 0 or U to approach some U desired. What I'm going to do is I'm going to make sure this U follows this U. Now both of them are same, so I will name this U as U virtual, because this is appearing as a virtual variable in this kinematics. So if we can control U, V, and R, then we can achieve this kinematics. So the reason behind why we took the derivative of yaw angle is, it will be evident to you now. Over here, we have Ex dot B. So we always want our system to be stable. For example, this is some constant C1. So if we can achieve this criteria, our system will be stable, right? So what I can do over here is that I can choose this U as a virtual variable, which will go to the kinematics. So this will become U virtual. I will cancel out these terms. So U virtual will become, this is minus U dB, so I will choose it as U plus dB, right? And then this is plus, so I will choose this as minus R E Y B. And then what I will do is I will choose some constant. I chose C1, so let me write it as C1 EXB, right? So now when I substitute this U virtual in this term, what will happen is that we will be achieving this result, right? Let me do it over here to explain it better. So this U, the idea is to make sure this U follows this U virtual. This is the main concept of this control for 3 degree of freedom shift. If we can make sure this U follows this U virtual, which goes into the kinematics, then we can achieve the position control. So once that happens, this u will be replaced with u virtual. So this will become u desired body minus r ey body minus c1 exp. And then we have these terms minus u db plus r EYP. So this term will cancel out with this one. This will cancel out with this one. And EX dot P will be minus C1 EXP. So we will achieve our asymptotic stability. Okay. Now we will follow this same process for the sway angle. But the problem is that it does not have any control input. So what we are going to do is use this yaw error for that case. So how we are going to design this virtual R virtual, same process, because our aim is to achieve this asymptotic dynamics, asymptotic stability. This is the same process. So R virtual will be chosen as plus R BB, right? And then plus. In this U virtual, if you note this, we controlled position along x-axis. So in this case, I will be controlling the position along C2 E Y B. So this will be my R virtual. Okay. So this is the basic concept, and I think this is the main concept of this 3 degree of freedom ship control, that how do we choose this virtual velocity and virtual yaw angle, and why we don't choose the virtual sway angle. The reason is, for sway angle, we don't have any control input over here. So we will be only choosing the virtual velocity for u and virtual velocity of r. There are some methods and some published paper in which they control this sway angle indirectly. How they do that? They use this u and r as a controller to this one. So they control u and r in such a way that we can control v dot, but that is not part of this video, because I just want to show you how to do the control for the 3 degree of freedom and achieve trajectory tracking. So now we have u virtual and r virtual. I will write it again, and let's proceed with the control design. So now let me rewrite the virtual control inputs which we derived for the control design. So we have this u virtual is equal to u db minus r eyb minus kx exp. And then I have this r virtual is equal to r db plus kr eyb. Don't get confused with this kx or kr. Previously, I think I used this constant c1. It's just constant, and it should be a positive constant. Just note this. So we have these two virtual variables. Now, the idea is to make sure this u follows u virtual. So I will define another variable, which is the error between them, u minus u virtual. Before that, just I explained in the previous slide, our aim is to achieve u tilde dot, which is the error of tracking error. It should follow a criteria. So let me call this kr. This is again a constant, u tilde. So when we can achieve this criteria, it means we are achieving the asymptotic stability. So this is our aim. Similarly, for r tilde, we will define r minus r virtual, and our aim will be to achieve its rate of change minus k. This should be ku, just to avoid confusion, kr r tilde. Okay, so what's the first step? So we will take its derivative because we want to achieve this criteria. So u tilde dot becomes u dot minus u virtual dot. We know from the dynamics that u dot is equal to 1 by n, right? We can see over here, 1 by n, mbr minus du, which is a constant, u plus tau u minus u virtual derivative. Okay. Now our aim is to achieve this dynamics right? This stability criteria, sorry. So I will substitute this on the left hand side. So minus ku u tilde is equal to 1 by m MVR minus du u plus tau u minus u virtual dot. So now I can derive this control input, right? I simply have to move all of these terms to the left-hand side and leave this tau u on one side. So we will achieve our control design. After multiplication of m on both sides, so here we had 1 by m, that will cancel out. So we have MVR minus du of u, not of u like times u. This is multiplication, not as a function. So plus tau u minus m u virtual dot. Now I can leave this tau on one side and move everything on the left-hand side and then simplify it. So I will achieve tau u is equal to minus k u tilde m minus MVR plus du times u plus mu virtual dot. Okay, so let me write these together. So what will happen is that tau u is equal to, this is multiplied with them, okay? So this will be m u virtual dot minus ku u tilde MVR plus du times u. So this is the final equation for the surge velocity control. Okay, here u tilde is actually u minus u virtual. So we have all these terms, right? We simply have to plug in these variables, constants, and terms in this equation, and we will achieve our surge controller. So that will actually control u dot. If you remember, we had this some function f of u and plus tau u. So we have achieved this tau u, and when we put this control in this dynamics, we will be able to control u dot. And what will happen with this u control is that we will achieve u approaching u virtual, because this u virtual appears in the kinematics x dot and y dot, and our goal is to achieve position control. Okay, so now we will follow the same steps for the yaw angle control and derive the controller TR. So let's move ahead. In order to design this tau R, so let me rewrite the R virtual equation. This was equal to R dB plus KR E Y B, right? So the first step is to design, to make this tracking error R minus R virtual, and our goal is to achieve this minus KR R tilde. So if we can achieve this, we will be able to finalize our controller. So taking derivative of R tilde, this becomes R dot minus R virtual dot. Then what happens is that we substitute this R dot. So this will be 1 over Iz. We know this from this equation. So M U V minus dr R, right, plus tau R. And then we have this derivative of virtual R, right? Now I will substitute this R tilde rate with this one because that is our aim. So this will become minus KR R tilde is equal to 1 by Iz MUV minus dr R plus tau R minus R dot virtual. Okay, so now simply I have to multiply this Iz throughout on left hand side and right hand side. With this term it will cancel out and it will be written over here. So let's do that in the next slide. So we will obtain the equation after multiplying Iz on left hand side and right hand side like this. So it will be minus KR R tilde IZ, and then we had 1 by IZ in fraction, so that will cancel out. So we will be only left with MUV minus dr times R plus tau R minus R virtual derivative. So tau R will be minus KR R tilde IZ minus MUV, because this will go to the left hand side or other side, and then we will be having this plus dr times R minus R virtual dot. But remember, we will have IZ over here. Forgot to write that, because IZ was multiplied throughout and it cancelled out over here, but it did appear over here due to the multiplication on right hand side. So TR becomes, let me take IZ common from this. So this will be R virtual dot minus KR R tilde minus MUV plus dr times R. So this is the controller for the yaw rate, which eventually controls the yaw angle. So now we have tau u and tau r, and we have designed the 3 degree of freedom ship control. And this control technique is often called as backstepping control. So because we cancel out these nonlinear terms and achieve our desired objective of this stable dynamics, where our aim is to achieve u tilde dot is equal to minus ku u tilde and r tilde dot is equal to minus kr r tilde. So we have to control or we have to design the control gains ku and kr as positive, and it should be sufficiently large so we can achieve this one, this criteria. So we are finished with the control design. We have done all the mathematics. Next step is to do these control implementation in the MATLAB Simulink, and then I will show you how I achieved the results which I showed you in the beginning of this video. So let's go to the simulation part of this video.
So I will be doing simulations over here. So I have opened this slide over here so we can look at it directly and implement our simulations. So first thing first, let's design this mathematical model. And for that, what we are going to do is we are going to simply use integrators and everything. There are actually two methods to do the simulations in Simulink. One is to use MATLAB function and design all these equations directly into it, right? You can open this and write all the equations in it. Like first you have to do first you have to write the dynamical equations and kinematic equations in this. Then for different parts, for example, for tracking error, you can define another MATLAB function block and all that. And similarly for control input. That takes less time, but it is difficult to debug the error in that. So what I normally do for my own simulations is to use the blocks. So I will be using the blocks over here because it is much easy to debug if there is any mistake in the simulations. So let's go directly into the simulations. So first of all, let's design the kinematics. So I will use integrators. So we have x1, x dot, y dot, psi dot. So let's have three differential integrators, and let's name them as x, y, and psi. So this is important to name them because sometimes we get this error in integrators and it is difficult to locate it. But when we name it with x, y, and psi or any variable you want, it is very easy to locate that integrator. Now, x dot is equal to u cos of psi minus v sine of psi. So it means we need a subtractor. So we will use a sum and change its sign from plus to plus minus to plus minus, right? And then we need a product because u is multiplied with the cos psi. So I will use another product here.
You can see over here product, and then we need another product for V sine psi. After that, what we need is cos and sine. So simply write over here. So cos, and then we need sine. So double click on this, and we can change it to sine. Okay, so now the thing is, in kinematics, we don't have u, v, and r, if you recall that. So what I'm going to do is I'm going to take an input pin, one with u, then another with v, and then another with r. Okay, so I will use this. So now the first one is u cos of psi. So I will simply multiply this u cos of psi. Psi is this integrator, so I will directly put it over here. The next one is minus v sine of psi. So I will take input from here, v, to this block, and then we have psi. So you can simply directly click over here, and this is a blue line, so we need to connect this over here. So and then I have to connect this pin over here as well. So this becomes x dot is equal to u cos of psi, and this minus v sine of psi. Okay, so let me use an output pin as well, and let me name it as x. Let's call it x. So, okay, this is giving me error because I have already used this x over here. So let's call it as pos x. Okay, let me do it for this pos y. And for this one, I have to use psi. So instead of writing psi directly, what I can do is I can give it a space, psi, and then space again. So there are 5 characters over here instead of 3. So this distinguishes from this psi. Now for the next one, we have this u sine psi plus v cos of psi. So again, I will directly take this summation from here. And now this is a plus minus. So what I need is plus plus. You can see over here. And the next one is u sine psi, but with the products. So I will add 2 products over here. Now we have u sine psi. So you click over here. So this comes over here. And then we have sine psi. What I can do is I can put a sine block over here and do the process again, similarly like the previous one, sine, and then connect this with over here. But just to make it simple, I will directly take the pin from here because I already have this sine psi over here. Okay, so one tip I will give you is that you should always write these signal names over here, X. You will find it out now why I'm doing this. So, because I have PSI over here, so when these connections are complex and there are many connections, it is difficult to follow. So what I can do is I can simply double click over here. So you see PSI appeared automatically. Similarly, I can name this as sine P, which is sine psi, and this as cos P. Okay. So when I double click over here, you see it appears directly over here. So I will not get confused. Similarly, I can give this as U name, this signal, and this as V name. You drag it over. So when I click over here, so U sine psi. So I will be sure that I'm not making any wrong connections. Now for this one, this is V. So I will connect it over here. You see V appear over here. And then we have this cos of psi. So I already have this cos here. I will directly connect it over here. And when I double click it, it shows me cos P. So everything is going well so far. And then this is PSI, and we only have R, so I will just directly connect it over here. Okay. So this was the kinematics model. It's really simple, and we don't have to like get confused in it. What I can do is that to make it simple, because now I will be making dynamics, so it gets really complex when all these pins are in one place. So what I can do is I can put this in one block and can drag this line over here. And after clicking 3 dots, it shows create subsystem. So it creates a subsystem, and let me name it as kinematics. So you can see over here that in one block we have all of these. Okay. So what's next is that let's make the dynamics. Adjust all of these over here. Okay, let me drag this to the top right corner. Now, next is our dynamics. So how are we going to make our dynamics in that? Once again, I need 3 integrators because I have U. Now this will give me an error because U is already written over here. So let me call this as with space. Let me call it U with space so it can distinguish it. Let me call this as P, this as R. Okay. So if we look over here, we have this 1 by m. So what I can do is I can input gain, which is a multiplier, 1 by m. Okay. Next is we have 3 terms and they are added together, but we also need a product. So let's do that. First, let me add a sum. If you look closely, we have plus minus plus. So plus minus plus, sorry, plus minus plus, right? And let me make it a bit bigger. So this. In the first one, we have an VR. So V and R are actually our states, and M is a constant. So for constant, I will add this because it is a multiplier, M. Okay, and then I need a product. So product here. So MVR, V, and this will connect it over here to R. Okay, if you remember, I told you to name these signals, so it becomes really helpful. And okay, let me add. Okay, I will do that later. I wanted to add output pins, but let's do that later. Next is minus du and then multiplied with u. So du is a constant. These constants are actually physical parameters of the ship, and we will be using Cybership II. And I will write its physical parameters later on. I will tell you how to do that. So minus du u. Now, this u will be connected over here. So you can see. So just to recall, let's rename it with u. Now it doesn't, when you double click over here, it doesn't show anything because the signal is directly going over there. But if there are some connections with this blue line, then it will work. Okay. And the next one is we have tau u, which is a control input. So we don't know that. So let me use our input pin tau u. Okay. Now let's expand this a bit so I can make it a bit better. Again, now v dot has 2 terms, and it has no control input. So I will drag this summer, but change it to 2 signs, which is minus minus. So I will double click this. This becomes minus minus, right? And now we have the first term as MUR. So M, and then over here UR. So U to the first pin over here, okay? And then R over here. Okay. So this is U and this is R. You see, now this double click works because we have 2 connections from this one line. And the next one is dV times V. So dV, I will have to change this from du to dV, and then times V. So this is V, and I will connect it over here. So if you double click, it's V. Now, one thing I missed over here is that we have 1 by m as well before integrator. So I can directly copy it from over here. Okay. Next is R dot. So for r dot, what we have is that 1 by iz. So instead of 1 by m, I have 1 by iz. And then we have three terms, plus, minus, plus. So fortunately, it is same as the surge velocity. So I will use the same summer. And then we have m times uv. So I will bring this product over here. This is u. So if I double click here, yes, it is u. This is v. You can see the pins are m, u, v. Then I have minus dr by r. So I will have to drag this gain, dr times r. So I click over here. Let's see if it's r. Yes, it is r. And then we have this tau r. Okay. So let me introduce another input. And let's rename this to tau r. One more thing. Let's use this output pins. So this was u. Let me write it as u as it is. Okay. I'm giving it as double space now, so we can distinguish between it. Or you can also name it something like u state, v state, like for example, this like v state. You can also name it like that. It doesn't matter, but for my convenience, I want to use this uv. And later I might change this name to different names. So let's see. So this is R. Okay. So now we have designed our dynamics as well. So let's do the same process once more. Drag this, create subsystem. Let's call it as dynamics. Okay. And I'll just simply enlarge this so we can see it clearly. So this is our dynamics. And just let me remove these pins now. I will tell you why. Because you will see over here that the output of dynamics, which is UVR, is the input of kinematics. And this was the major challenge, if you remember from the beginning. We wanted to design U virtual and V virtual, R virtual. So this was the reason. So we have to control, just to give you a review of the control design, that we have to control UVR in such a way that we can achieve the position which we want to obtain according to our mission. So this is the mathematical model. And let me put it in one more block to call it as a 3 degree of freedom ship. 3 degree of freedom ship model. Okay. So our modeling is done. Now, what we are going to do is we are going to design the controller. So just to like change this formatting, I don't want to see the content preview. Yeah. So this is our 3 degree of freedom ship model. So this was our ship model. Actually, I extended the screen and I removed the notes from the side because it was occupying too much space. So now we can see clearly what is happening in the Simulink model. So this was our 3 degree of freedom ship model, which we did previously. So one thing I missed over here is that I'm obtaining these outputs x, y, and psi over here from the model, but I did not took this output of velocities because we also need that. We will find out that later on when we will need it. So I will just simply put 3 outputs for the velocity and make these connections u, v, and r. So now I will have 6 outputs and 2 inputs over here. Okay. I can also modify this slightly. Why? So it looks
much better now. ESI, ESI. Okay, looks much better now. So now what we can do is that we can do the simulations from we did define the definition of tracking errors, and then move towards the control design and obtain these tau u and tau r. Or what I can do is I can directly implement these control inputs and then go backwards. You will see what I mean here. So let's do the control design firstly. So if you can see in the notes which you may have written, we have tau u controller, and there are actually 3 terms. So and they are subtracted and added with each other. So I will use a summer over here. So first term is plus, then minus, and then plus again. Okay. So this was for the controller tau u. Let's not think about the ship model at the moment. And the first term is actually m times u virtual derivative minus ku u tilde. So I need another summer over here, which should be the difference between the derivative of u virtual and u tilde. So we have this term, and then we have this gain m. Okay, gain m, and then it is multiplied with u virtual. So let me use a constant block over here. I will tell you why we do this, because I will be assuming that u virtual dot is actually 0. We are not using any filters, and the concept of that, how to obtain the derivative of virtual velocities. So I will assume this as 0. And after that, we have gain k. You can look in the notes, gain k u, and it has u tilde as an input. So u tilde is once again a difference between real and virtual. So what is our real? Real will be obtained from the output of this ship model u, and u tilde is equal to u minus u virtual. So I will just make a virtual input port over here, because we have the equation for this, which I will design later on. So this was the first term, and then we have minus mvr. So I need a product where I can multiply v and r, and m is a gain. Okay, it is becoming like this terminology, and I have this m. Okay, and it is multiplied with v and r. So this is v and this is r. Now you understand why I took output of this uvr like this, because I needed these pins. So this is minus muv, mvr. The next term is plus du u. So du is a constant, we know that. So du is a constant times u. So u is already this line over here, so I will simply connect it like this. Okay, and the output of all of this equation is actually tau u, tau u. Okay, so we have designed our controller tau u. I want to put this in one block so we don't get confused. So once again, create subsystem, click the first option, and we have tau u in one block. First one is u virtual. So if you look this u, and it goes to second pin. Second pin is over here. So I can just write this as u. This third pin was v. This fourth pin was r. So I can just move it to the left-hand side so it looks a bit better. And we don't need to change the number of these pins. So this is the controller for tau u, which is actually search controller. Okay. Now the next one is tau r. So we can do similar modeling once again. So I'm just looking at the equation. Once again, we have three terms similar to this one. So I will just copy this summer. Uh, in fact, let me do it over here. So I just have only one block for the controllers. So I have this for tau r. Output will be tau r. The first term is iz times r virtual. So instead of m, I will have iz. Then I need a summer with plus minus, which has r virtual dot r virtual dot. Okay. So once again, just to tell you that I'm using this constant block because later on I will assume this as 0. We are not using filters, which is actually a bit challenging work. You can design Kalman filter or commanded filters to obtain this value, but I will assume 0 and then simulate our ship. So the next value is minus kr. So k underscore r, or you can directly write it as kr, and then r tilde. So this is r tilde, which has the value of r tilde is actually r minus r virtual. So I will just introduce r virtual over here firstly in the subtraction. This is r minus r virtual, and r I already have over here. So I will just obtain this from this input. So this was the first term. Next one is MUV. So M with negative sign. I need a product UV. So this is U. It's connected over here. Then I have this V. It is connected over here. Okay. So this is MUV. And then I have DR times R. So I need to change this to DR and times R. Okay. So just to check the equations, so I will just rename these signals so I don't make any mistake. So I can see here, this is U, this is V, all right, this is R. Similarly, this is U, is all right, V, R. So all the equations are correct. So now we have control inputs tau U and tau R. Instead of writing it as surge controller, I will just name this as control inputs. Okay. Now I have control inputs for our ship model. But now the issue is that I don't know what is my R virtual and U virtual. So I need to design that as well. And if you remember from the simulations, we have already designed the control loss for that. Now this first way is U virtual and the last one is R virtual too. So just so to adjust it, let me rename this from 5 to 2 and it will automatically move upwards. So now what I'm going to do is I'm going to connect these inputs to the ship, but I cannot simulate it because I still don't have R virtual and U virtual. So next step is to design these virtual variables. So if you look in the notes, we have U virtual is equal to UD in body minus R EY in body minus KX EX in body. So I have actually three terms with addition and subtraction, plus minus minus, plus minus minus. Okay, that's simply this. And then I have UDB. So let me use this input UDB, UD in body. Okay. The second term is the product of R and EY in body. So let me use this product term. Okay, I already have R, so I will connect it over here. And then then I need is EY in body. So let me use another pin. EY in body.
I don't have these terms, so I use input terms, which I will design later on. And the last one is kx, which is a gain. It must be a positive gain, k underscore x, and it is multiplied with ex body. So when constant is multiplied, by the way, I did not explain this, when constant is multiplied with one signal, so we can directly use this gain, but if there are variables, so we should use products. We can also do this similar thing for the constant ones as well, like this. I can use a product block. I can use product block. Okay, and then I need constant block. So I'm going to click something else. Okay, and I can write kx over here. So this is also valid, but it is much better, or actually I prefer this to use gain for one signals. So this is actually my u desire body minus ey body times r, and then this last one is ex in body. Okay, so the output is actually u virtual, and this signal is actually r. Okay, so now let's use this in one block with the previous times. So I have this u virtual, right? And I have these signals which I will be designing later on. Now let's design R virtual. Okay, it has only two terms. They are added together, added with each other, plus we R desired body, R desired in body, plus gain K, which is K times R, and EY body. So I already have this EY body, right? So I do not need to add another pin. I can directly take it from here. I need to check this. This is right, but I know this is correct from the mathematical derivative and the equations I have written with me. Let's move this R over here so it can look a bit better. And the output will be R virtual. Okay, so we have U virtual, R virtual as well. But now the issue is that we don't have UD body, RD in body, and these tracking errors in body. So these are U virtual and R virtual blocks. Okay, let me move this R to the last pin. Okay, so now I have these virtual velocities as well. You can see we are going in right direction with all these connections. Now what we need is we need to design these UDB and RDB. Now let me set up the pin numbers because this looks a bit strange to me. So EX, which is tracking error in body, this should be the first pin. This should be second, tracking error of Y in body, third, fourth, and let's leave this as fifth. So now we have to design these tracking errors in body. So I have these equations already with me, and we also derived these equations. So let's design these equations. So EX in body is actually really simple. We need a sum. If you look at the equation, it's really simple. Sum plus plus, which is then obtained using this tracking error EX. So we need another sum, which should be EX. plus minus. Okay, so let me move it over here. So we need a sum, but it's a sum of product terms. So we also need a product over here. So product of EX. So let's ignore this EX at the moment. You will know why, because I want to make a separate block for it. So let's take EX directly from here. And then we have cos of psi. So I need cos block, cos function block or cos, and it should have an input E psi. So let me get with as a input over here, and this should be psi. Okay. Plus EY sin psi. So again, a second product of EY sin psi. So this should be over here. EY, and then I need sine. So I will just double click over here, change it to sine, and psi. So it will be from over here. Okay. So this is EX in body. So let me make it as EX body, right? Similarly, EY body, so that is actually slightly different. EY body. The difference is that it is minus plus, minus EX sine psi, and then plus. So the product of minus, right? And then product of what? EX sine psi. So this is EX. Let me rename this signal and connect it over here. Let's double click it. Sorry. So yeah, this is EX. And then this is sine psi. So sine psi is over here. So I can directly see plus product of EY cos psi. So EY is over here, right? You can see like this, and cos of psi. I'm not writing the signal names because it's obvious and I can directly see over here. So EX first signal, EY second signal, and then PSI, which is psi. So this is my tracking errors in body. Let me put this in one block. I'm putting these in separate blocks, so it will be easy for me to debug it if there is a problem, because MATLAB will directly tell me that the error is in this place or in this block. So I can directly open that. So I have EXB, so which I can connect here, right? And now I need UD in body and RD in body. So UD in body is actually, again, a sum. So let me just copy it directly from here. I will copy all of this because it is similar if you look at the equation, and just rename these. So this is UDB. Now you will see the difference is we have XD dot and we have this psi desire instead of psi. So this is psi desire. Okay, and EX, instead of EX, we have XD dot, right? And then multiplied with cos psi desire dot, psi desire plus, and then Y desire dot times sine psi desire, and then we have this UDB. And RDB is actually 0. RDB is 0, so I will choose this as constant and just give it a value directly from 0 block. Okay. I already explained this to you, why it is 0, because this is the difference between the desired position. Or you can say we need derivative of psi desired dot. So it actually becomes double derivative. So we assume this to be 0. Let me put this in another block. So you can see we have this subsystem for UDB and RDB. So we have got these blocks as well. Let me remove this. What I can do is I can simply copy this and put it in the same block as well. Instead of making two blocks, I can copy it in this block. So I don't get confused with all these blocks. So I can simply delete this one, and now I have 4 pins from one block, right? Really nice and beautiful, I should say. It's really going really well for us. Now I have these inputs, ex, ey, psi, xd dot, yd dot, psi desire. So if you look at this, these are obtained directly from desired position because ex is x minus x desire. So let's make a block for this as well. It should be really easy and straightforward. Let me make it. I don't use these circular blocks, by the way. Mostly I use these rectangular ones because this is much better for me. You can use the circular ones as well. So this is ex, this is ey, and this is e psi, right? So this is input x minus x desired, right? Desired. Then we have this input y minus y desired. And then I have this psi, which is the angle. I simply need to connect this over here. So psi and psi desire, right? I got these tracking errors. So let me output these to ex. This becomes ex. So it is giving me error because I have used ex over here. So just let me make it like this. Give it a space. Now this should be EY, so I will give a space over here so it can distinguish between the characters. And this should be E psi. I don't know if we will be in need of E psi, but let's design it. So now I have all these three, and the psi value will be directly coming from the output of the ship plant, and x, y also from ship plant, and desired values we will be giving it from our trajectory. So create subsystem. Let's delete these pins, and let's format this content preview. Okay, so we can see here we don't need this e psi, so I will just remove this and use a terminator because I'm in no need for it. Actually, it is needed over here in RDB, this value, but its derivative is almost zero. So I use this constant block over here. Where did it go? Yeah, here. So I use this constant block. So that's why we don't need it. So we have EX, we have EY. These are tracking errors. Okay. So simulation is almost done. Now I just have to connect the pins. So X, Y, psi, let me adjust these pin numbers. So we can, let's put desired values at top. So I will just change these names. Y desired to 2, psi desired to 3, 4, 5, 6. Yes. Okay. And what I can do now is that, okay, XD, YD, and psi D, these are from the trajectory. So we need a trajectory.
and we will use some trajectory. If I remember, yeah, we will use a trajectory which I did simulations before at the beginning of this video. So I will use that trajectory. So we will get desired value of x, y, and psi d. X, y, and psi, they will come from this value. And now we need x dot desired, x d dot, y d dot, psi desired. So these values will also be from our trajectory. So I have already written its function. I will directly copy it over here just to save our time. Okay, so let me make these connections first. So x will be here, y will be here, and psi will be here. So let's extend this psi. And this is for x. So you may have heard about this inner loop and outer loop. So that concept is also demonstrated over here. You can see these velocities, they operate as inner loop control, whereas this position, this operate as a outer loop. So next I will make this MATLAB function for the desired trajectory. So let's do that. So I already wrote this code for MATLAB function, which shows the trajectory S shape. So you can see it over here. We have U, which is desired surge speed, amplitude, time. And then I defined position, velocity, acceleration. We don't need acceleration, so it is 0 along x-axis, and some value which is obtained using taking derivative for 2 times of this desired position along y-axis. So this is just mathematics. We have this heading, psi desired, which is a tan 2, dy d, which is desired velocity along y-axis, but its derivative, and similarly dxt. We don't need this heading rate, which is set to 0, and I already explained that to you previously. So why I use MATLAB function over here? Because it is easy to write trajectories in this, and it will be much easy for me to change the trajectory from S shape to circular or any other thing. So for trajectories, it is recommended to use MATLAB functions. These other blocks, they are fixed, so we don't change them. So I use these blocks, which you saw already over here. But for trajectory, which we often change from one trajectory to another, so I use MATLAB function. So let's make these connections. So x desired with x desired, yd, psi, d. Okay, now we need this x desired dot, so which is actually dxt, derivative of xt. So let me connect it, or I can connect this directly, dy with this one. And then this is psi desired, not dot. So let me connect this over here, and let's extend these so we don't get confused. And then I have psi, which should be connected with this one, which is the output state, not from the desired block. So let's connect it over here. So we have done all these connections. Our simulations are ready. Now what's next is that I need to add the parameters, physical parameters of the ship. What is mass? What is du value? dv? Similarly, I also need these control gains over here. We need ku, kr. In virtual velocities, we need kx and kr. So let's do that. I have written the code already, so I will simply show it to you and explain the important points from that. So this is the code, and these are the parameters of Cybership II. So our mass is 23.8 kilograms, Iz, which is yaw inertia. These are all physical parameters you can find in books or research papers. So I already found these online, and I took from there. And then this is the reference S-shaped trajectory. So this is actually a code for that. So you can simply copy it from here and paste it into the MATLAB function block. Otherwise, we don't need it over here. I just want to show it to you over here. These are the control gains, which we can tune and set to different values. They should be positive. This is the important point. We can increase and decrease according to our simulation results. These are initial conditions which we need to input to the integrators. By default, they already assume the values to be zero. But if in case you want to set these initial conditions to some other values, you can change it over here. But you have to edit the integrator block of that. For example, this is x naught equal to 0. So this is for the x integrator in the model of the ship. You need to double click over there and write x naught, and then you can simply change the values over here. Still, we don't need that because by default, MATLAB assumes that the initial conditions are 0. Then we have to simulate our system. So I set the simulation time to 3 minutes, which is 180 seconds. And then there is this command, sims. I said this sims is actually a variable name. So I can choose any name for this simulation or anything. The important part is the right-hand side. So this sim actually simulates the Simulink model which we designed. So this is the code for that. And now we will run this code and see if we have done everything successfully and correctly. So now I need to stop this video over here and share the screen once again because I have to share both this code as well as the Simulink block to you during the simulations. I tried to share the Simulink block diagram and code side by side, but the visuals were very small. All these blocks were like this, so I thought maybe it would be best to show it in bigger like screen like this, because you may not be able to see it in YouTube when I upload this video. So I will just keep switching the screens. So I showed you the code, and let me go back to that again. So this was the code which I showed to you. Few changes which I made from the previous code is that here it was written kpx, so I changed it to kx in this line number 28 because in Simulink, when I put that gains inside that, I wrote kx. Similarly, k underscore y, k underscore u, k underscore r. So I changed these values, and we had this virtual dot for u and r. I set that to 0. If we want to design some filters, we can design a filter and place it there and simulate according to that. But I want to use this as 0, so it will have no influence on the simulation results. These were initial conditions, and I added this code for the plot. So if you need this, you can take screenshots from here. This is for the HD plot and all these commands. This is for data preparation because I want to show you the results on the surface. So all this is a code for plotting. It's not like very difficult. So yeah, let's go back to the Simulink block. I want to show you one point, these blocks. So when I use the code for simulations, so I have to add this block, which is to workspace. So you can write like this, to workspace, and it will appear here. Then you can double click it and give it some name. So let's say I give it to a name as pause X. So I have already added that over here. So I will write as pause X state. And then we have these formats. You want to save it as a time series or array. I always choose array. And so I choose array. So I chose this over here. Then click apply. Okay. So you will have these kind of blocks for X, Y, and yaw. So I already added that to save our time. So you can see here, this is pause X array 3D. Similarly for Y, similarly for this angle yaw. Once again, I have to add these for velocity. So U, V, and yaw rate. Vel underscore U means velocity. U, velocity V. Similarly, I can add this for control inputs here. So let me add this for control input to workspace. So the first one, tau u, is actually surge velocities, surge controller. So surge controller, save it as an array, apply. So I will keep this as a connection over here. The second one is tau r. So that is your controller, your rate controller actually. But let me write it as your rate controller. Okay. So this is for control inputs. Similarly, I have to add it over here for desired position. So position XD, position YD, and YOD. These are for desired. The reason behind adding these blocks is to have this data in our workspace so we can play with it and make our plots. So let's go back to the code. So this is the code. Once again, parameters, which are physical parameters of our ship. This is reference trajectory, which I used in the MATLAB function. So if you don't want to write here, you can simply delete it from here. Okay, let's delete it. Control gains. So these are control gains over here, kx, ku, and then ky, kr. Virtual dots, I set to 0. Initial conditions, MATLAB assume it as 0 by default. But if we want to change it, we can change it over here. But we have to write this variable in the integrators of the model. Let me show it to you where. So this is the model. If I want to change, if the position initial condition, so I will just double click over this and X naught over here. Okay. Similarly for Y naught, this Y naught, Y0. Okay. And similarly for this one. So this is how we change initial conditions. But by default, MATLAB assumes it as 0. So let's get back to 0. In case if you want to set some values, you can set directly over here. But it is much better if you define a variable and write variable over here, because you can easily simulate it from the code directly. So the setup for the simulations is done. So let's do the simulations. Let me run the simulation and see what happens. Yeah, we can see the simulation result. Let me drag it over here. Can you see it now? I hope you can. I will simulate it once more. This is the first plot. Desired trajectory versus stranded trajectory of our ship. So let me simulate it once more. It is dragging the results on my second screen. I don't know why, but I will explain the results to you. So this is in blue line is our desired trajectory, and this maroon line or brown line, this is the trajectory followed by our ship. So initially there is some error, but after tuning the control gains, we achieved this desired result. And as promised in the beginning of this video, these are our simulation results. So this is 3D plot. You can see here. Sorry, this is 3D plot. So you can see the result over here. And this is the top view of the same plot on the right-hand side. So this is the top view, and we can see our ship is following the path after some time. This is position along x-axis, which is followed here, and then this is position along y-axis. I'm not explaining the code for these plots, but if you want, I can explain it to you. Just to give you a brief explanation, in MATLAB, when we plot a figure, so it shows us just one figure, but we can use subplot commands. So what a subplot command does is that it plots the multiple results on one figure. So you can see we have 4 figures over here. For this one, I use a grid of 3 rows and 2 columns. So we have actually 3 rows and 2 columns, and this first one occupies the first 2 rows, and this occupies the next same 2 rows, but of the next column. And here we have results for the position X and position Y. So yes, let me think if I have some points if I want to discuss. Yeah, the key point is which we should know is that here I assumed virtual control, virtual surge dot, which is derivative, as 0, and R virtual dot as 0 as well. You can extend this controller by designing the filter for this. Maybe you can design Kalman filter, first order filter, or commanded filters, and then achieve the filtered output and give it at this pin. So that will be like modified controller from this one. The basic concept will remain same. You only have to change this block for that. Another thing you can do is to extend this controller is to add disturbance in this mathematical model, because in reality when ship is like moving in the ocean, there are ocean currents. So there are many disturbances appearing on the ship. You can add disturbance over here and then design disturbance observer based control. Actually, that is my major. I design disturbance observer based control. So if you need any help with that, let me know. I can help you with it. Perhaps I should design some short course for that and upload it here. But anyways, that is another idea. You can also do state estimation, because sometimes sensor outputs are not good. So with state estimation, you can modify this controller. Nonetheless, the basic concept which I wanted to teach you in this course is that we need virtual controls for the kinematics. Because if you look here in kinematics, there is no control input, but dynamics has two inputs. So we need to design these two inputs in such a way that it controls UVR as a controller to our kinematics. So that's all. If there are any questions or any ambiguities or confusions, please let me know. I will try to explain it to you. I may have made some mistakes in the control design when I was doing mathematics. I reviewed these videos and tried to fix them. But let me know if I have made any mistake, and I will try to correct those and try to explain it to you. But yeah, this is all about the 3 degree of freedom ship control. And we simulated, first of all, we did mathematical modeling and control of the ship, and then we simulated it in MATLAB Simulink. So I hope this helps you, and I wish you all the best. Thank you to be with me and watch this long video. I hope it helps you. So have a great time. Goodbye.